Hello, it's David at DCES UK, and today I'm talking about my fans. No, not you horrible lot out there who generously contribute toward the beer donations, but actual physical electrical fans, and specifically this fucking monster, which I pulled out of a Swiss residential Leamington town centre apartment block recently. It looks like it collected a few dings along the way. Oh, I can already hear you all out there asking, why would you witter on about such a topic, David, you well-hung, ruggedly handsome, trim-buttocked prince of a man? Well, thank you for noticing. But there are a couple of very interesting things of note about the installation of this particular beast, so let's not write this video off as being a load of boring old blarney just yet, even if we will all do that long before the end, I'm sure. We were first called out to this fan back in 2017, when it had stopped extracting the damp air or poo pong of the apartment's occupants. This is an industrial fan, of course, and was mated into some proper metallic ductwork located above the ceiling of this apartment, which had been refurbished back in 2004. Yes, none of your cheap plastic FlexiDuct or wheezy 20 quid tool station inline tat here. This thing will give a proper blowjob for your money. In fact, to illustrate that, we can rate these fans on the internationally recognised blowjob enthusiasm scale, where we find those cheap, flimsy plastic type affairs ranking right down at the bottom end. It's not quite Catholic nun, but it's not far off, certainly somewhere around the wife's typical stance whenever such is requested, whereas an industrial fan such as this is right up at the top end, close to desperate crack whore who'll suck a golf ball through a garden hose, so long as you keep dangling that 10 quid note. Of course, there are mid-range domestic entrants such as the 100mm mixed flow, but the point is we're talking poles apart between a fan like I have here today and one of those rubbish 20-odd quid energy wasters that will do little to snort up and spout out your stinking farts. So this thing had been doing its thing from 2004 to 2017 when we were called out to investigate why it had stopped lifting the nasty niffs from the homeowner's nostrils. We diagnosed a bad run capacitor, which is this bugger housed in the IP box on the side. That box is part of the manufactured assembly, by the way. It's not something an installer has added on. It's there to house the connection block and capacitor. On a single-phase motor, the run capacitor energises a secondary winding to create a rotating magnetic field and get the thing spinning. A motor that ain't turning may just be down to a bad cap. At the time of our visit in 2017, we lacked the means to test a capacitor, which is when I went out and snapped up my Klein CL3200 clamp meter. There's a link to that video in the description. These days I have several meters capable of measuring capacitance, but back then I'd never needed it out in the field, and indeed I've not had much cause to measure such since, save coming back to diagnose another fault on this fan now in 2022. So let's have it out for a closer look. This is a 2 microfarad capacitor. And if I put it onto a capacitance meter here, we'll see what we get out of it. And 1.75 microfarad. Well, that's a little out of tolerance and suggests this replacement cap may itself be on the way out. Not that it's anything to do with the failure of the fan, which has an internal fault. Something's shorted inside the fan housing here 5 years on from our previous visit, and now it trips the breaker when switched on, regardless of any external components. Let's have a bit of a play with this capacitor though, and I'm going to use my lovely Robin KTS 1625 for this one. If this capacitor is still good, which it appears to largely be, then on a 250 volt IR setting I should be able to charge it up. I won't go to 500 volts as the component is rated at a maximum of 440. But when I start the test, we should see the voltage quickly rising on the right side of the display, while the resistance reading starts low and climbs as the capacitor fills with a charge. Eventually, it'll hit the 250 volt ceiling, where the charge in the cap matches the input voltage from the Robin, and both displays will level off. It seems the Robin has put out about 280 volts, so that's the charge that should be in the capacitor. The display here is maxed out at 250. As I release the test button, we get an audible alarm indication. I'm going to switch the instrument from IR to voltage here, just to silence that. The alarm is because when the IR test stops as I release the test button, the Robin is no longer putting out a voltage, which matches the charge in the capacitor. Indeed, the probe's dropped to 0 volts. So we now have a potential difference between the charged capacitor at 280 odd volts and the tester at 0 volts. The capacitor then discharges back into the tester. The robin sees that external voltage on its probes, and because the selector switch is still on IR, which is of course a dead test, it sounds an alarm because you wouldn't want to IR something that's live. Until the capacitor has discharged to below 20 volts, the robin won't let me repeat this test. I'm going to do it again just to show something else. When I charge the capacitor, I'm applying a positive voltage from the robin's point of view. When the capacitor discharges, it shows a negative voltage on the display. That is, of course, because the DC voltage is now pointing in the opposite direction. Previously, the tester was putting out plus 280 volts into a capacitor at 0 volts. Now it's the other way around, with the capacitor putting out plus 280 volts back into the robin. And because it's coming back in the opposite direction to how it went out, the robin shows it as a negative voltage. The robin's at 0 volts, the capacitor is 280 volts below it from the robin's 0 volt perspective. Just to show that this capacitor can hold a charge, and that such will feel very fucking positive if you happen to grab the wire ends, let's juice it up now. There, that's a charged capacitor, 280 volts or whatever. How long it can hold that charge for depends on numerous factors, and I wouldn't like to guess. Let's stick it onto this LED light bulb to discharge it. And this will be one of those blink and you'll miss it moments. Well, that wasn't very impressive. Let's have a slow motion action replay. There, that brief flash is all you're going to get, because although it can store enough volts to give you an unpleasant whack, it hasn't got the minerals to drive any real load. And this is only a 1.8 watt LED lamp too. As a side note, incidentally, these are quite interesting decorative lamps I picked up from IKEA a few years ago and never did find an application for. Big Clive has a video where he performs a teardown on one, and that's linked in the description. But enough on the capacitor. It's reading a little low for what I'd expect, but it's clearly still operable. I've already changed out the motor for a wholly new unit on site, and let's hope that one lasts as long as this did, 23 years being a pretty good stint for anything with moving parts, I'm sure you'll agree. You can see it's still free spinning, so it's not seized, but I'm not going to disassemble it. There's nothing here I can service. It's an extractor, I'm afraid. You may be thinking this is all well and good, but why was an industrial fan such as this in use in any domestic setting in the first place? Certainly, we've come across few such examples in our time, but they tend to get installed in apartment buildings where more than one room is being served, and here's where it gets interesting. No, come on, bear with me. This fan and the ducting arrangement served 2 bathrooms in this case. Whenever the lights were switched on in either bathroom, the fan would operate. The electrical arrangement by how this worked was somewhat clumsily installed by being shoved into a large IP enclosure on flying leads hiding in the void near the fan, but I was able to access it and break it down. And look, I've even built a little demonstration mock-up for you miserable bastards. On the left is the light and switch for bathroom 1, on the right is the same for bathroom 2. The extractor, represented here by this equipment fan, will operate when either light is switched on. Observe, motherfuckers! If I switch on bathroom 1, both its associated light and the common fan actuate. If I switch on bathroom 2, its associated light and again the common fan actuate. With both light switches off, the fan is off. With either or both light switches on, the fan is on. Electronics boffins will recognise that what we have here is a binary OR gate as represented in this truth table, where one or the other input or both need to be on for the output to cause the fan to fanny. The observant and sober among you will have spotted that this functionality is being achieved here through the use of a relay, so let's break this bollocks down into a wiring diagram to see exactly what's happening. Let's start with the relay, which has 8 terminal pins and consists of 2 separate double pole switches, each with a common terminal, a normally closed terminal and a normally open terminal. For those not familiar with relays, this is similar to the white plastic light switches I'm using here, but it's all contained within the relay housing. You can think of the normally open and normally closed terminals as L1 and L2 on a 2-way light switch. These switches here account for 6 terminals, and the remaining 2 have a coil across them, in this case a 240 volt coil, but you can get relays with all sorts of coil voltages, with 5 or 12 volts perhaps being the most common, where a small control voltage can operate a higher voltage or current switching load. But let's not get into that here. Suffice to say that when the relay is off, i.e. the coil is not energised, There is continuity between the common and normally closed terminals of each internal switch, as shown by the orange and green paths here. You may wonder why I've crossed these lines on this diagram, but these are the pinouts, layout and numbering of the actual relay I have here today. If we energise the coil by placing it between line and neutral, then the coil acts as an electromagnet and pulls the contact away from normally closed to normally open, thus giving us continuity now between common and normally open. If we stop providing current across the coil, then the magnetic field collapses and a spring pulls the contacts back to normally closed. So now that we know how a relay works, let's place it into a circuit to control our 2-room extractor fan setup. Here we have the switch and light for bathroom 1 and for bathroom 2. This is the fan, and everything in this grey section is internal to the relay as just described. So if you weren't paying attention a moment ago, now you're fucked. In the real world, a competent designer would incorporate a fuse for the fan along with an isolator to allow it to be shut off for maintenance. But for the sake of simplicity, I've omitted such from my diagram, in just the same way as how a dickhead builder or bathroom fitter would omit them physically out there in the wild. At present, neither light switch is on. Each associated light bulb is therefore off, and as per the OR truth table, a 0 and a 0 means that our fan is working like Nigel. That is to say, sitting there looking like a mechanical asshole and doing fuck all. Let's start with throwing the switch for bathroom 2, as that's the simpler operation to describe. Closing the light switch opens a path on line to both the light and to the normally closed pole of the relay. Bathroom 2's light comes on, and because the relay is not energised at this time, the normally closed terminal is connected to the common terminal. Therefore, we have a current path through the relay. Because the fan is connected to both common terminals, we also have a path to the fan, and so the fan starts sucking out the stench of our lager-sodden foamy shit to an unsuspecting outside world. Bathroom 1 is a little more complicated, but from the same start point of everything being bone idle, again like Nigel, we throw the switch and the associated room illuminates. This time we also have a connection to the relay's coil, so current will pass across that, causing a magnetic field to form. That magnetic field will drag both relay switches from the normally closed to the normally open positions. The relay switch on the right, shown in orange, isn't going to do shit, as nothing is connected to that normally open terminal. However, the green contact on the left now flicks across to its own normally open terminal and creates a path of continuity between that and the common terminal. Now current can flow from the normally open terminal on the left through the relay to common and again out to the fan, as the fan is, well, commoned to both common terminals. We can determine from this setup that bathroom 1 has priority. Not that it really matters, but if bathroom 2 is in use, then someone entering bathroom 1 and switching on the light will always cause the relay to switch over to the bathroom 1 path. I've waffled on about priority controllers before in my video about my gyro switchover unit that gives my electric shower physical priority over the EV charger to keep my maximum demand down, and although that's not quite the same as this, it's not friggin' far off. The main difference with the gyro is that it uses a current sensing relay, which means both loads get power, but it's only when the priority load starts taking more than about 10 amps does it mechanically switch over. So this arrangement is pretty simple, yet clever, and can be used for switching any common load between two inputs. The only problem here is the lack of a timer to hold the fan on for a while after the lights have been extinguished to ensure the room is fully vented. Well, chill biatches, because we can add in an external motherfucking timer easily enough by placing it before the fan itself and feeding it on a permanent line so that it always has power. Now when a switch line hits the timer from either bathroom light switch being on, it will output to the fan and set it spinning. When the switch line drops low, the timer will hold the output to the fan for a predetermined period to suck out your stench. On this particular fan, a humidistat timer had been fitted, albeit with the humidistat disabled, which makes you wonder why the installer splashed out for this when straight timer only modules are available. Remember, this is located above a false ceiling, so there's nothing for the humidistat to pick up on anyway. Testing shows this humidistat timer to be faulty. There's a rogue 50 volt sitting on the switch line coming out of this module, so something's fucked inside it. When wired in, not only does this rogue voltage cause the LED lamp in bathroom 2, which is on the default path, to flash while off, but the timer itself never shuts off. It may be that the fault current from our failed fan balked something in here, but whatever, this timer is toast. This Swift Air controller connects in the same way as the humidistat timer, so swapping it out is straightforward. When power is now applied with the Swift Air in circuit, the fan starts spinning, and that's because the timer goes on a self-test for a minute. This fan's a bit rattly with its loose grill, so I'm going to pop on my knobshine mug to shut it up. That'll be winging its way to my competition winner very soon. I hope you entered in my Nick Bundy video, because by the time this gets edited, it'll likely all be over. Okay, after the self-test ends, all accessories are off. Flicking either light switch causes the fan and associated light to come on. Only when both lights are extinguished does the timer start. This is currently set to minimum time, so should hold the fan on for about a minute past lights out. This stop clock, you perhaps can't see, will tell us how long it's on for. While it's running, I'm going to use my Hioki here to show that the fan output of this timer is around 240 volts between line and neutral. We're looking at the bottom scale of the Hioki, and 0 is at the rightmost position, so the needle is indicating what we expect to see. What do you think is going to happen when the timer stops? You may be in for a surprise. I sure as shit was when I fitted this thing on site. Okay, we're passing the minute mark, and sure enough, there we go. The clock says 1 minute and 9 seconds, and we can see the needle on the Hioki has returned to its 0 position and the fan has stopped. So what's wrong with that, you might well ask? Well, let me grab a non-contact voltage detector. Yeah, bitch! Why does this still appear to be live when off? Well, if I keep my Hioki probe on fan line but move the other probe from fan neutral to supply neutral, well, look at that. Fan line is live at 240 volts. But how can that be if the fan isn't spinning? Well, let's move the Hioki between fan neutral and supply neutral. And here's Johnny. What the actual fuck? This timer hasn't shut off the supply to the fan. Instead, it's gone and cut off neutral. It's only the fact that there's no longer a potential difference between line and neutral that stops the fan from spinning. Any idiot who doesn't check for safe isolation would think the fan isn't powered, but it's very much still live. I don't know if I just have a faulty unit here, or if this Swift Air contraption is made for something specific that works in a different way, although I doubt it. Certainly the point of sale didn't mention anything about it stopping the fan by breaking the neutral path. Everyone knows you don't fuck with neutral. You don't fuse neutral, you don't switch neutral, and you don't backfeed neutral, because any of these things can make something appear to be de-energized when it is in fact live on both poles. Several days later, and I have managed to procure this Manrose timer, which looks suspiciously similar to the Swift Air. Still, Manrose are a venerable ventilation vendor here in the UK, so let's see if this one behaves a little more in line with expectations. Oh, how smo. I'm seeing that rogue voltage on switch line again, and it's causing bathroom 2 to flash. You know, maybe that's not a fault after all, but a characteristic of these Manrose products with such a low wattage LED lamp. I'm getting about 36 volts with this lamp connected. Let's remove it and see what happens. Stick these back on here, and oh, you crikey, look at that, we've gone up to about 110 volts now. It's like there's a minimum load this timer needs to work with, although Christ knows why. Let's see what else I've got here. Maybe we should try bumping it up to a 3-watt LED lamp. Oh, stroby. I should put on some 90s Prodigy to accompany that. Let's see what figure we're getting out of this thing now. We're hovering around 51-ish volts. It's jumping around a bit. Let's see what happens with a 4-watt lamp. I've got a 4-watt just here. We'll see what this one does. Oh, that's interesting. It's got a more permanent glow. It is. I don't know if the camera's going to pick it up. It is quite flickery, so it's obviously flickering at a higher frequency. and the voltage is around 86 volts with that one. So it goes to show that the different electronics in these lamps has quite a difference in effect on this timer. I'd be interested in hearing from electronics boffins as to why that is. The largest LED lamp I have to hand is 7 watts, and I'm going to have to use an E27 to E14 converter to get this into this ridiculous little lamp holder here. But there's no flashing and no glow to report, and we're reading just 6-ish volts now, which ought to not to excite the driver electronics. Obviously a compact fluorescent or incandescent lamp won't be bothered by a bit of rogue voltage on the switch line, but it seems these timers don't like very low loads on their input. Still enough of all this. Does it work in the way we expect? Let's turn off the light, start the timer. The fan is fanning, and hopefully after, well, a minute-ish we should have something to report. We're reading about 240 volts line to neutral on the timer output to the fan, and we're just waiting for oh, there we go, the fan has just stopped, 49 seconds, so that's not too bad, and we saw the voltage drop down to 0 on the fan output. But has it killed the fan by pulling the neutral? Let's take a look. There's nothing on fan line and neutral, nothing on fan line with respect to supply neutral, and nothing on fan neutral. So the Manrose is behaving according to expectations by cutting the supply to the fan. Marvellous! I wonder if the gizzards are the same in these Manrose and Swift Air affairs. Let's pop the Manrose open, see if we can see what's ticking inside this thing. I think this plate's just sort of stuck on. Yes, it is, and well, there's plenty of whistles and bells on show in there. I think the PCB is just glued in, but because this is a working timer, I'm not going to expend too much effort trying to get that out. We know this works, so let's just leave that intact for the moment, but we'll pop open the Swift Air and see what that looks like inside. Okay, this should just pop open in the same way. Oh, well, there's not a lot to see there, is there? It's not a complicated board like the, or as complicated as the Manrose, which is obviously a double-sided board. This has got a couple of retaining screws in rather than being glued in, so we'll have them out and take a peek at what's on the other side. Okay, I'm going to put some close-ups of what I'm seeing on the screen here. But on this Swift Air timer, the fan terminal has a trace back to the permanent line terminal, so it's not switching the fan line is very much a design choice. This is how it was made to work. Instead, you have fan neutral connecting to supply neutral through this BT131 triac, and that's what's making and breaking the neutral connection. This is pretty iffy, it seems to me. Cutting neutral means an apparent dead fan remains live, and its neutral is now floating at 230 volt, waiting to catch out the unwary. Here's what I don't like about this thing. Had I used it on site as I intended, then as the designer and installer of a fan circuit employing this product, would I have fallen foul of BS 7671? Consider these two regulations. 132.14.1. A single pole fuse, switch or circuit breaker should be inserted in the line conductor only. And 530.3.3. A switching device shall not be inserted in the neutral conductor alone. If I provide a certificate for my work which has my signature on it that says I've complied with BS 7671 with no deviations, could this Swift Air product land me in hot water if someone subsequently gets a shock from live equipment they thought was dead? Swift Air is a brand owned by Fans for Less Limited, so I quoted these regulations to them along with a query as to why it's even designed in this way. After all, perhaps there's something I'm missing. Their response?
There shouldn't be any power to any item when maintenance is being carried out. Surely you fit an isolation switch which would be off if any work was being done.
Yes, there should be an isolation switch. I quite agree. I always include fused isolators on the fans I install myself, but how many extractor fans have you fellow Sparks come across out there that wholly lack one? It's not uncommon for builders, bathroom fitters, DIYers and even shifty sparkies to stick in a fan directly off the lighting circuit with no isolator. Also, consider who may be performing maintenance on a typical bathroom extractor. Someone unskilled may prise off the cover to remove fluff from the thing without thinking of flicking an isolator, even if present, while being wholly unaware of and not equipped for performing safe isolation procedure. Even a professional spark may get lazy and assume the thing is off when called out to attend to it. More fool them if they choose not to test. But the point is, it seems strange to have a product aimed at the domestic sector that pulls the plug by breaking the neutral. When pressed further, they went on to provide this spell-checked challenged response.
We don't recommend anyone installing an item on their own, and all warranties are void if this is the case. All electrics should be carried out by an electrician. You can switch from a neutral to control a fan, and is done this way on a lot of units in other parts of Europe.
Well, maybe, but Europe give less of a shit about polarity and aren't working to BS7671. Yes, you can physically switch a neutral to control a fan, but why would you think it's a good idea? Manrose didn't with their external timer. The expectation from most people's point of view is that if you want to stop something, you kill the power to it and not the return path from it. My expectation as an electrician and as a homeowner is that if something is off, then it's fucking off. As for the warranty, well, who gives a flying fuck at a rolling donut? They're saying an electrician should be trusted to install a thing. I'm saying that as an electrician, I wouldn't want to install it, as there are 2 wiring regulations I would appear to be putting myself on the wrong side of. Instead of offering a technical reason as to why it's designed as it is, Swiftair seem to be suggesting that it doesn't matter because it's down to everyone else to ensure the power is properly off. The designer and installer are responsible for ensuring isolation is available. The maintainer is responsible for ensuring they both use that means of isolation and test for dead accordingly. Why should Swiftair have to incorporate any thought into how their product works if everyone else does what they ought to? Assuming safety is everyone else's responsibility is an interesting take. I'm not sure the likes of HSE would agree if someone got fried by assuming a fan that looked off wasn't.
The trouble with fatal events, from aeroplane crashes that kill hundreds to some lowly homeowner getting electrocuted, is that it so often isn't down to just one smoking gun, but a combination of errors that happen to link together to form the perfect conditions for a catastrophe. The HSE could easily have a case where they're carting a corpse out of a bathroom and tut-tutting over the fact someone pulled the cover off a fan for maintenance, exposing live parts when not equipped with a working voltage indicator, who failed to follow safe isolation procedure, exacerbated by the builder having omitted to fit an isolator, exacerbated by there being no RCD protection, exacerbated by the external timer pumping out power to a fan that looked for all intents and purposes like it was off. Recommendations? The dead guy was perhaps an idiot. The builder may share the culpability, if he even left any paperwork admitting to having worked on the electrics, but the fan controller itself offered a false sense of security that no power was present, and Swiftair designed it that way. I put a poll out on Twitter to see what others thought, and maybe I loaded the question, but the majority of respondents in the twattersphere figured neutral switching was not a good idea, and nobody seemed to have a valid reason why this device would be made to operate in this way. Completely Electrical STEM Show referred to regulation 463.1.2, which seems to permit neutral switching in a control device for lighting circuits, which seems an obscure arrangement, although that is for lighting, and the wiring diagram still shows a switching arrangement on the line. Of note, the last line of this regulation states, switching of the neutral shall be in compliance with regulation 530.3.3, which, if you'll recall, says a switching device shall not be inserted into the neutral conductor alone. So that's handy, and about as transparent as dog shite, as usual with BS7671. On this Swiftair gadget, the switching device is very much in the neutral conductor alone, as we've seen that fan line out is hardwired to line in on the PCB, so 463.1.2 doesn't seem to get them off the hook here. Outspoken YouTube and Twitter gobshite, Jamie Blatant Sparky, chimed in to say it's to prevent inrush current across the coils and is also permitted for contactors and relays. I'm not so sure, and I can't find anything that shows switching neutral is advantageous for coils, but if anyone knows anything different, then do shout about it in the comments. Jamie may be onto something, as the PCB in this Vent-Axia has a direct connection from line into the fan motor, and it's the fan neutral that's switched. But this is an individual unit, not an external controller like the Swiftair, which might not even be located in the same room as the fan it's controlling. Fans for Less can't or won't explain the choice of product design, and I think it's safe to say that the expectation for those of us who may be tasked with installing this thing is that it would turn the power on and off to control whatever one may choose to hang off it, and not that it would keep the power on permanently but cut the return path. Swiftair? Fucking buyer beware in my humble opinion. Stick with the Manrose model if you want things to work as most people think they ought to. Going back briefly to relays, and one thing to note when using them is that when you energise a coil, you create an electromagnet, as I've already stated. But when that coil becomes de-energised, the magnetic field collapses, and a collapsing field generates a voltage. This trait is useful in applications where you're actively trying to generate electricity from magnetism, but in something like a relay, it's an unwanted consequence of the coil switching off. The voltage generated can spike for a very short time into hundreds or even thousands of volts, and is what's called a back EMF, because it travels back towards the voltage source that has just been removed, similar to what we saw with our capacitor discharging into the Robin tester earlier. In electronics, it's common to install a diode, or diodes in AC, across the coil to block this back EMF and stop it spiking into something that won't take kindly to it. The relay I have here has this diode protection built in, but many don't. Moving on to something simpler with this Vent-Axia 100mm timed fan, which is one I installed in 2018 and was called back to recently to replace as it had gone faulty. Normally we stick with the likes of Vent-Axia and Expellair as their venerable and reliable brands. Sure, you pay more for them, but they tend to last and to not go squeaky or rattly quite so quickly. Surprising then that this one has failed, but let's have a look and see if we can see why. I've jerry-rigged the switch line, so if I plug it in, then it should operate. And it doesn't. Kind of works with a bit of a helping hand though, so maybe we're looking at a bad capacitor again? This is a 2-speed fan, and the jumper here selects it between low and high. If we follow the PCB traces, that jumper position seems to select either this capacitor or this capacitor, so these two caps are directly related to the speed control. Okay, so it's not working at one speed. Let's change the jumper and see if the other speed is functional. Yep, there you go. So this could be down to a failed capacitor here then, although it's unusual for these film caps to go bad. Let's see what we can see with my TIS E217. This capacitor, which is working, is marked as 824, so that's what, 0.82 microfarads, 820 nanofarads. Well, let's see. That seems to check out. This smaller cap, which may be bad, is marked 474, so 470 nanofarads. Let's give that one a whirl. That's not looking so good. I think we'll have that out for a closer peek. Yeah, this capacitor is definitely balked. The nearest thing I've got on the shelf is this 500 nanofarad thing, but this is only to prove a point here, so I'll wang it on for shits and giggles. Okay, new capacitor clumsily shoehorned onto the PCB, and I've set the jumper to use it. Let's plug in and see if we get spinning or smoke. Hey, well there you go. If I get me the right part, I could bring this fully back into service. Or I could just move the jumper over to the other speed and bypass the faulty component. It goes to show though that if you get called out to a faulty fan, switching the speed selector, if it has one, may bring it back into service. Anyway, it's all a boring subject perhaps, and maybe not the fanny action you were looking for. And by fanny, I am of course referring to the British definition of a lovely lady's front bottom holy hole haven, and not the American interpretation of it being everyone's rusty rear cat flap. Nonetheless, what got lost in translation on my first visit stateside a few years ago will stay lost, and is best forgotten by all concerned. And so ends yet another video. Churning them out lately, aren't we?
Yes, exactly.
What's this wee business? what are you doing?
I don't know.
We have some shout outs, not too many because we have just done a video and done some shout outs, but there are a smidgen of generous people whom we would like to thank. Starting with Stephen Sherry.
Yep.
Stephen Sherry, who is a whore.
Yes, I recognise that name.
Yes, thank you, Stephen. Not your first
Thank
contribution.
you.
So, yes. We also have a virgin in the form of Viv and Marto. Perhaps that's two virgins. A duel of virgins. A duo of virgins.
Yes. A pair.
A pair. Good word. I like that. Viv and Marto, who say, have a frothy facial from us. Well, there you go. You've got to have something to pluck out of your beard, haven't you, Nigel? Did you ever shampoo your face fungus?
No, I don't even.
You really should do,
my head.
because there's all sorts of dried sperm in there.
Just a bar of soap does me.
Right, there you go. A dial of soap for Nigel. What kind of soap do you use?
Imperial leather.
Get you, your highness. Fucking hell.
It's the cheapest soap we can buy.
Jesus.
Used to be posh, it's not anymore.
You can't tell me you've got no fucking money and you need to pay your right. Imperial leather, what an asshole. And finally, not finally, because there's Nigel Tupman.
A name
a name
that's been read many times.
That crops
Thank you, Nigel.
Yes. Who makes the comment that you've got the best crack on YouTube.
Well, I'm not sure he's ever seen my crack. Unless
we've all seen your crack on previous videos. Yes. It doesn't hang out as much as it used to.
Yes.
But we've all experienced
days.
Your crack. We must do a VR video, a 360, featuring your builder's ass hanging out of your trousers. That'll be an experience, won't it? That'll get us off YouTube. He spells crack, of course, in the Irish sense.
Yeah, crake.
Indeed so. And finally, for the coffee shouts, the actual coffee stuff, we have Donovan's Alarms. Is there a finer alarm company?
Fuck no.
There you go.
It just isn't.
In fact, Donovan's Alarms, if you want to put that quote on your website, you have testimonials and stuff.
Nigel from DSES says, fuck no. There is no finer alarm company.
Yeah, I expect to see that on your website in short order. And one final special mention to Tim from Sheffield, who likes to send out written praise via snail mail, if you remember such a thing. Thank you once again, Tim, for your letter from Sheffield.
Well done, mate. Someone who can still hold a pen these days.
Always nice to. You normally types them and beautifully typefaced. I'm not sure if it's a typewriter or if it's like a
printer.
Yeah, but it's like in a courier font. I believe it does look like it's like wow, that's.
Only Dave could get turned on by a font.
It's just nice to see someone who can string a sentence together.
Yes.
Few
grammar
seem to be able to.
And spelling seem to be.
Dying art
these days.
I'm afraid so. But Tim, who's obviously of an older school of thought, thank you for that. The last one he did write, it was short and brief.
He didn't say go fuck yourself, savoury.
I don't think I've experienced him using foul language.
Right.
Or if he does, he might have done actually in the past, but in a very justified way. So thank you, Tim. And so ends another stint in our coffee hole. We've got to go and do a job now, haven't we, Nigel?
Yeah.
Which we would record, but this new camera's out of memory space, so long.
Yep, no memory, no video. You better get them ones off.
Yeah. We lose it all. Bye-bye.
See ya.